We're off. Okay. So we're talking about temperature scales. When in the previous video, we just talked about temperature in Fahrenheit and Celsius. Now let's talk about absolute scales. So Kelvin and Rankine scales. So in the absolute scales, you've got, so show me here. In the absolute scales, these are also called thermodynamic scales. You've probably heard of the Kelvin scale before. Kelvin is the SI scale for temperature or for absolute temperature. Rankine is the imperial or the English scale for absolute temperature. And I don't know why I pulled the camera up on me because I'm just about to go right back here to, I can get my mouse. There we are. I'm going to go right back to the document camera. So Rankine and Kelvin are, again, what we call absolute scales. There is a temperature we call absolute zero. Absolute zero. I cross my Z's, by the way. Absolute zero. That occurs at 0 kelvins, which is 273 degrees below zero on the Celsius scale. About 273. You should have learned about this in a physics class. Or I'm sorry, chemistry class. Maybe physics also, but for sure should have learned about this in the chemistry class. Uh, this is also 0 Rankines. That is the, again, kind of the imperial scale that is set at absolute zero, 0 Rankine. There are no negative values on the Kelvin scale or the Rankine scale. Now, to get from Kelvin to Celsius, it's a difference of 273, give or take, degrees. To get from Rankine to Fahrenheit, it's a difference of about 460 degrees. So Rankine is 460 degrees below the Fahrenheit scale. So to get from Fahrenheit to Rankine, you would add 460 and vice versa. So, how cold is absolute zero? Well, if you think of the Fahrenheit scale, it's an unfathomably cold temperature. I think the surface of Pluto we estimate to be in the mid 300s Fahrenheit, -3 Fahrenheit. So it's really, really cold. Okay. So, what does that mean for us? Well, what we need to know here is that again in a Rankine scale there's no negative value. So if I'm multiplying by a temperature and that temperature could potentially have a negative value in an equation, that negative sign might change or alter how that equation is going to behave. So it's always appropriate or always safe to use Kelvin or Rankine. It may or may not be safe to use Fahrenheit. It just depends on the situation. Now, Fahrenheit or Celsius. There are a lot of times we will use Fahrenheit and Celsius. How do we get back and forth between them? Well, we've already mentioned it's a difference of 273 for Celsius to Kelvin. It's a difference of 460 for Fahrenheit to Rankine. The same conversion factor you've used since probably elementary school to get between Fahrenheit and Celsius. It is 9/5 and then add 32. You subtract 32 and divide by 5/9 or multiply by 5/9, whichever order of operations you got to do, whichever way you need to go. Because the Rankine and Kelvin scale both intersect at absolute zero, to go from Rankine to Kelvin, you just multiply by that 9/5 or 1.8, and you can go between those scales easily. You don't have to add the y-intercept there of 32 for that one. Okay. A change in Fahrenheit is equal to a change in Rankine. The same way a change in Celsius is equal to a change in Kelvin. You've probably done this before in a chemistry class, but let's just see. So if I've got T1 is, I don't know, let's say it's 75 degrees Fahrenheit. And let's say we turn on the air conditioner and T2 then becomes, I don't know, 2 degrees Fahrenheit. We cool it off just a little bit, right? And so what is this in Rankine? So we add 460 to that. So that is 5, 3, what is that? 535. Does that look right? I think it's right. Maybe it's not. You can tell me down in the comments if I got it wrong. And we add 460 to this one, so that's going to be like 532 rank. Okay. So if I take delta T, that is T2 minus T1, right? So if I take 72 degrees Fahrenheit minus 75 degrees Fahrenheit, that is a minus 3 degrees Fahrenheit. It's a 3-degree Fahrenheit drop. It is also the same if I took 532 Rankins minus 535 Rankins. That's also going to get me minus 3 Rankins. We could do the same thing with Celsius and in Kelvin there, right? A difference in Rankine is going to be the same as a difference in Fahrenheit. And the difference in Celsius is going to be the same as a difference in Kelvin. Okay. So I can use Fahrenheit and Celsius so long as I'm multiplying by a change in temperature. There's going to be lots of times throughout the semester we're going to multiply by a change in temperature. So a change in temperature, I can just multiply by um, Celsius temperatures or Fahrenheit temperatures, same as I could multiply by change in Kelvin or change in Rankine. But if I'm just like saying the ideal gas law, remember in the ideal gas law, you had to convert Celsius temperatures to Kelvin. Same thing in the English system. You'll have to convert Fahrenheit to Rankine when I'm using the ideal gas law. So if I'm just multiplying by a temperature, it has to be in an absolute scale. Okay. So what else then? That brings us to pressure. What is pressure? So I'm going to work us pretty close to manometer, and I'm probably going to record manometer videos a little bit later in the week. But let's see if we can get close to it. Pressure is normal force exerted per unit area. So let's say we've got it's summertime for us here. Maybe you want to go swimming or you want to go diving. Maybe you're ambitious. You put on a tank and scuba gear or maybe just a snorkel and you go diving. Or you again go swim in your pool. As you get further and further and you get deeper and deeper, you'll notice force being applied. And that force is perpendicular in all directions applied to you. Pressure is force exerted by a fluid per unit area. Right? So it is the result of the fluid molecules bumping into you. And as those fluid molecules bump into you, they apply a force to you. And if I add up the force caused by all of those molecules across the entire surface area that they're colliding with, eventually you get a total amount of force over that area. That's force per unit area. That is essentially what pressure is it's the result of all of the fluid molecules that you're exposed to bouncing off of whatever it is they're bouncing off of. You inside of a can, whatever it may be. And it's going to be perpendicular. It's going to be normal to whatever it comes in contact with. That's the reason for all these arrows here on my terrible drawing that I've drawn for you. Um, Units of pressure, right? I think that's what I'm doing here, right? Units of pressure, which I'm going to go to my document camera here to do that. So we talk about units of pressure. L1, this is page 3 of something. Pressure units. Okay. 1 Pascal, named for a scientist named Pascal. I don't know much about Pascal. I know some about some of the other scientists. I don't know much about Pascal. Pressure is, so the Pascal is the unit of pressure in the SI system for pressure. Um, this is force per unit area. So it is 1 Newton per meter squared, the unit of force divided by an appropriate unit of area, force per unit area. Now, you can further break that down. You can always break that Newton down into its base units of kilograms, meters per second squared. A Newton is force times it's force, so it's force is mass times acceleration. So a Newton breaks down to a kilogram meter per second squared. And then that's to get a Pascal, that's per meter squared, which if you cancel these things out, what do we got here? Let's see, these are both in denominators. This is 1 kilogram per meter per second squared. Now, you don't have to memorize that. In fact, I don't have it committed to memory. What you want to do, though, is start being comfortable saying, well, what is pressure? Pressure is force per area. So that means that's Newton per meter squared. You don't have to remember that a Pascal is a Newton per meter squared. You just have to remember pressure is force per area. And then the SI system, you break those down into base units. And then you can break all base units all the way down to mass, distance, and time. That's always true unless there's a temperature involved, or there are a few other base units you can't break down further. But almost everything can break down into a combination of mass, distance, and time. In the SI system, that means you can get all the way down to kilograms, meters, and seconds. 1 atmosphere, which is the amount of pressure exerted upon us by Earth's atmosphere at sea level. Which, if you look on the inside cover of your thermodynamics textbook, you should find conversion factors, and down here is pressure. And so I know you can't see that very well, but 1 atmosphere is 101,325 Pascals, or 101.325 kilopascals. So it's a natural number. It's not an exact number. However, there is a unit you will find in many thermodynamics textbooks. Ours does not typically use it, but if you will occasionally encounter the bar. 1 bar is an even 100,000 pascals, or 100 kilopascals. That is a bar. It's a very common unit of pressure you'll encounter. That's a nice round number, approximately 1 atmosphere. We're a little above sea level where we live here. We're not like really up high like in the mountains. We're just a little above sea level. So there's not as much atmosphere above us. So we would be slightly less than 1 atmosphere, but we'd probably be closer to a bar around here. I'm sure there's a joke there, but I'm going to leave it alone. In the English system, we use a unit called PSI, and I'm going to call it PSI-A. 1 atmosphere, it's about 14.7. I think it's 14.69 something. Look at my conversion factors here and double check. I think it's about 14.696 if memory serves. And if I could flip my text to the right page here, that would be helpful. Pressure, 1 atmosphere. 14.696. Yes, I should have trusted my memory. 696. It's going to list units there of PSI-A. PSI-A is pounds per square inch. The A stands for absolute. We're going to talk about in just a second. That is, you can just simply treat that as pound force per inch squared. That's what PSI is, pounds per square inch. That's pounds force per square inch, PSI. These are the basic units of pressure that we'll work with. In all cases, every unit of pressure should be able to be converted to some unit of force per unit of area, some distance squared. Lucy, can you jingle your bell somewhere else, please? We keep bells on our cat's collars so we know where they're at. They're little ninjas. So anyway, if you heard the jingle there, that was our good friendly Lucy jingling her bell for us. Okay, what's next here? Hi, Lucy. Do you want to say hi? Come here. You guys have seen Izzy. This is Lucy. She's adorable, isn't she? Will you be good? Go be good, please. Go play. All right. What's next? Let's see. That's actually not a bad place to stop. My timer did go off because we wanted to talk about units of pressure, which is what we did. And then the next thing is we're going to talk about absolute and gauge pressure. So that's coming up next.